It gives me great pleasure to introduce our first speaker, Dr. Bengt Fellenius, who I met when I was a graduate student at the University of Washington. Since we met, we've exchanged many email discussions about deep foundation behavior and interpretation, and he's helped me a great deal. And certainly I've learned so much from the writings, but more importantly, I think we've developed a nice friendship, and that's very meaningful to me. And so it's a very great pleasure to introduce Dr. Bengt Fellenius to you all, who you all know no doubt about his excellence in deep foundations engineering and analysis. I think his work speaks for itself. With no further ado, please join me in welcoming Dr. Bengt Fellenius.
Thank you, Armin. It's a pleasure to present this. It's a simple case history that I enjoyed very much when I came upon it by accident, more or less, 2 years ago. In connection with ongoing construction in the city of Gothenburg, or Göteborg, in Sweden, involving tall buildings and highway viaducts and very big construction project. They decided to do a static loading test there. In Sweden, they don't normally do static loading tests, but here they felt they needed one. I didn't know of it, but I got an email from 2 students, Fredrik Edvardsson and Johannes Pettersson, graduating as civil engineers. They were doing their Master of Engineering report. It's a part of the studies. And they had done this test, but now they were unsure about the analysis of it. So they asked for advice, and I gave them some advice, and I said that for fun, they could invite people to predict. Prediction is always interesting, I think, and enjoyable. So very simple on the soil condition. It's right there. It's a 90-meter thick deposits of soft marine clay. In other areas, it can be deeper than that, and it's high water content, close to the liquid limit, high plastic limit, and the upper 20-30 meters is by definition soft. Quite compressible, normally consolidated too. So foundations will have to be on piles, and it's common to use floating piles. Surprisingly enough, there are very few studies that they made locally in how these foundations behave. Structures are generally behaving, but as to why and how is not generally known, so they now needed this test. Well, this is a picture of the test pile with the jack here. That has a concrete platform built, cast around it that's not connected to the pile. Here is a test with 2 cross beams and reaction piles. The piles themselves were precast concrete, 50 meter long, 5 pieces, and they were spliced with a splice commonly used in Sweden. A couple of competing splices too. Here we see the pile toe, and that's the gauges in the pile are get out and covered, protected by a half tube, and it goes all the way down to the pile toe here. I mentioned that I suggested that they do a prediction, and they sent out to mainly Scandinavians, but also internationally, inviting people to predict the load movement curve. And this is a compilation of the predictions that came in. No surprise, there's quite a scatter, only that I kind of wonder about these fellows and these fellows too. Predictions are hard. The best predictions that you read, particularly academic papers, are the ones made after the test. Now, I've added some spice to this and asked the two students to, Fredrik and Johannes, to ask every predictor to also tell from his curve what is the capacity of that pile by his usual definition. And these dots here, they're the deliverer. Now, this is not a prediction, mind you. It's an assessment, what they think from their curve, be it coming up like this or something like this, what the capacity would be. No one needed to say what the definition was, if it's an eyeballing or something else. But we obviously have a scatter on these people looking at a long pile in clay. I've done that before. I think it's very revealing, almost scary. You have here, for instance, a test that I have 94 people. Sent them a curve from, and actually they had predicted the response of a test. They knew the soil. And I sent them the actual test curve. And I say, what is the capacity of this test pile? Assess it. And this is the results. It's an enormous scatter. I've done that on an event that took place in Brazil, Araquari, where the organizers said before, capacity is 10% of the pile diameter. Now predict the load movement. I don't agree with that so-called definition. So I wrote to all the predictors, got the names, and said, now if you agree with this 10%, tell me, and if you want another value, indicate it. And here to the right is the response. Some people are down there, some are up here. 7 of them agreed. That definition, incidentally, has its origin, they call it the Terzaghi definition. Terzaghi was a sharper guy than that. So I started searching for what's the origin of this reference, and I found it. It's a discussion type paper that Terzaghi wrote in 1942 on a discussion in the ACE about capacity, that perpetual question that Sam Pajkowski showed us a little bit this morning. How do you define capacity? Now, Terzaghi did not define it. He said that, fellas, don't even bother to talk about it until the pile toe has moved at least 10% of the pile diameter. That's a very different definition, I'd say. That is no Terzaghi 10%. Then Terzaghi said, don't talk about it until you have moved it 10%. Then it can be smaller or larger. He didn't say that. So people still, even in the Eurocode, they have now the 10% criterion. But this is beside the point. Let's get back to this actual 50-meter long test. Why I was particularly interested in it is because I was born about 1 mile away from the test site in that city, a little bit earlier there. And I did my main part in my PhD work, 4 years in the field, was about 3-4 miles up the river from this site. So in a sense, I was nursed on that lake. So it was exciting, not just to give advice to a young student, but to actually see how the test came out. So here's a compilation of the load movement, and it goes up. And when we get to here, it's suddenly brittle type failure, and they keep pumping, and the load is constant. Actually, they had no load cell. That's one miss in the planning. Always have a load cell. Because now when they're pumping and the jack is expanding, there's friction in there, so the real load is really smaller. And as it happened, this one strain gauge level was very close to the pile head, and it actually functions as a load cell, and that is the true load. Before this, the it's no problem. It's a steady situation. Now we look here at the load time. And you can see that they tested in a different sequence early and changed it for the later. It's not good if you have instrumented piles. It didn't do much of a problem here. The strain gauges, I want the next slide. Microsoft PowerPoint is not responding. We'll see if we can make it respond. Yeah, clever me. I don't know what I did. Strain gauge record. This is the first one here is the one nearest the pile head. About a meter into the soil, there's nothing there to give shaft assistance. Then we have the next one, and the next one, you see the depth, and I changed the horizontal scale. When you combine them as the last slide, you see that the uppermost one is pretty well a straight line it should be, and then you can see that there's more and more load coming down to the lower portion of the pile. We know the strains. There's an uninteresting information. What do we need strain for? We needed to find the stiffness in the pile. We need the stiffness to convert to load. And the easiest way, and that stiffness is pile modulus and cross-sectional area. In a precast concrete pile, as in this case, area doesn't change. In a board pile, we have a bit of a problem. Now, for the gauge level, that is not affected by shaft assistance. The best way is to take the so-called secant stiffness directly. That is plotting the load divided by the strain, load divided by strain, which is a secant, plotted against strain. And in this particular case, it comes out that pretty well in straight line. The slope of that line is, we can take a linear regression or whatever, and we find out the stiffness, EA, of the pile. For the gauges further down, we can't use the secant. We have to take the so-called tangent, which is the change of load versus change of strain. That's the differentiation. If you have some inaccuracy, uncertainties in the measurement, you're going to see a bit of a scatter up and down like this. This is pretty normal, but if they had used a load cell, they would have been closer. But it gives the same value of the stiffness. We're not interested in the concrete modulus, but knowing the steel area, we can back calculate the concrete modulus. You have it down there. A little bit high because it's a high quality, high strength concrete. You may also be surprised that its modulus is linear with strain. That depends on the mineral. This is a granite bedrock, crushed stone they have in there, and the sand, the same origin. The modulus doesn't really change that much with strain. Some other concrete made of different kinds of mineral will have a sloping line, so the modulus reduces. That's why, with increasing load. That's why it's useful always to use the secant and tangent modulus method to try to find the stiffness as a function of the strain. Now you measured strain. So now you have, for every load applied to the pile head, at every gauge level, you know the load, because it's that stiffness times the strain. And we have the load distribution. can look at the actual I'm trying nice now to tell them to change the slide. And this is the load movement curve again. And when looking at it, I know from the back calculation, we did not have a telltale to the pile toe. We should have. On a long pile, you'd like to know the pile toe movement. I can make an approximate calculation of how much the shortening of the pile is now that I know the load distribution. You essentially take that area and and look at the accumulate the strain. You know the what the strain means in shortening, and you know how much the pile is. So I can figure out within tenth or 2 millimeter of how much the pile has moved. But it would be nicer to have a telltale. At the maximum load, the pile had moved close to an inch, 22 millimeter, I think. And the pile head, sorry. The pile toe moved about 3 millimeters. That's not very much. Sure, that's the movement here. When it starts going here, we have so rapid changing here, so that those records are not really meaningful. So at this point, I know the movement of the toe is 3 millimeter. I know the loads, and the next step is to figure out for every length, every pile element, be it 1 meter or half a meter, whatever, what is the load movement information? And for that, I need what's known as TC and QC functions, what the load versus movement is, and it can have many shapes. I pick one point, I usually call that the target point, and it can be anywhere. I pick it here, and depending on what method, and they are several types here, 5 I'm showing, they all have in common the same target point, and going through there, I can come up with that the potential curves are spread out, fanned out like this. So now that's general. Which one should I take in the evaluation? I can take this one, which is Van der Veen method. It's almost elastic plastic. I can take a hyperbolic shape, and all of these are hyperbolic. All of these follow the power function, which is called ratio or Gwisdala. Here's another one that is Brinkansen. Doesn't go past the maximum load. Here is Chinese strain softening method. And then we have Vijay Vajia's strain softening method. And in an actual analysis, here, an example, as a pile, I'm looking at this element and at this element, and from a strain gauge there, and I have the movement. I believe this pile is a test where we have a telltale at every strain gauge level. So we know at each of these 2 element level, the actual shape of the curve, these squares, dots here. Now, and taking all of these various TC curves, it's not too hard to fit anyone to the beginning of a maximum point. It's a little bit harder after, and it's usually only one that fits, in this case, a method called developed by a fellow named Raman. And the other element has a different, slightly different set, and the main point being, when I know the actual load movement in one point, I can simulate that and then make the jump of imagination, say that is representative for the next couple of meters above and below in the soil layer. And in this particular case, see if I press another button, if I can make it shift. I have another slide coming, and I can see it even, but it... Okay, it made it. Computers. Life was so good for the first 20, 25 years of my practical experience when I didn't have to bother about them. Here is, for one layer, what I came up to that would fit. And actually it fitted all through the pile. It's a uniform soil, very uniform from top to bottom over the pile length. And this is the toe response. It follows the Residual ratio function, and because it's a little bit curved here before it linears out, is a typical record of a pile with some residual forces at the pile toe. And the procedure to come up with these two TC curves, TC and QC curve, is that a faster way of shifting slides here? Or I guess if I can see. Yeah, here we are. Okay. I start with the gauge level closest to the pile toe. And playing back and forth, I know with the pile toe assumption and the very short distance of shaft resistance there, until I have fit the load movement for that gauge level. Then I go up here and do the same thing. Then I go here. When I work on this one, anything below this gauge level I don't touch. So I go stepwise up until I have the pile head. And I have then simulated the entire test, all the measurements. I'm trying to... I think this is set up to give a minimum time for each slide. So if I want it faster, it won't do it. That's fine. Now, the back calculation of load distribution that I now fitted is this green line here. By the best fit to the measured load movement with the observed strains. Now that means that I have a beta coefficient in ineffective stress analysis that starts out with 0.43, which is a high value for a soft clay. And it goes down to 0.18 or 0.15 down here. In a uniform soil, it is not likely. It's true from the analysis. Everything fits. But if I apply the assumption, which is a fair assumption, I think, that the uniform soil and we should have the same beta coefficient all the way through, become 0.19 all the way through. Then the difference here is the residual force in the pile, which is the same, the difference is this red line going down here. That is residual force in the pile, and now my analysis has established approximately what the residual force would be. What causes it? Well, the site has been settling a little bit for the past 8,000 years. And back in these early days when I was working a couple of miles up the river, and we measured this. I'm pecking away here, trying to shift my slide. Okay. Now, I don't know, Armin, what I can do. I'm losing time. Anyway, here. This is a slide I could have skipped. See next time I don't shift it yet. There, 1968, we had similar piles, and we measured the increase of force with time. And I'm just showing that the distribution of increase, distribution with time. And now see if this can be shifted. Where did that friendly man go who could possibly change the slide? How do I get the next slide here? No, back up, but there's still a slide to go. Okay, this is what I want to see. This is the 1968 case of different days after installation. Now there we had a good resistance down here, so it's looking for a neutral plane down here. But in the upper 20 meters, the 50-meter pile in soft clay all over agrees very well, and then we have essentially a neutral plane and a positive shaft resistance here. So it agrees. I think the approximate distribution of residual forces is there, and we have that to contend with in planning to use the test results for a longer or shorter pile, and with for the forthcoming construction. I don't know to what extent they do that at this time, but it gave me a lot of satisfaction and quite enjoyable case goes through. Good data. The two civil engineering students did well, and they are now actually, I'm happy to say, pursuing a technical career. The basic finding is that when reaching that plunging, some people call it capacity. Well, they could. I don't mind. I don't care about capacity. I find it a useless concept for any use. I'm looking at the 22 millimeter movement and the 3 at the toe, and I will do the analysis from there. We established the stiffness, the axial stiffness of the pile. If we had gone by concrete strength, we would have been about 25–30% off. And established what strain softening function that fitted best to the data. Always nice. Yeah, more of that. And we could use the test data to satisfactorily find what the residual load distribution is after 200 days of waiting between installation and actual testing. If we had waited another 100 days, or they had waited, it would have been a different distribution and a different evaluation directly from the strain gauge data, whereas the assessment after would have been the same. So, thank you for your attention.